What's up, everyone? We're finishing up. We're almost at the end. We're going to start talking today a little bit about the trace and the determinant. Or actually, more accurately, we're going to talk about the trace. Then we're going to get started talking about the determinant, which we'll finish up with next time, and it'll serve as a nice little capstone final piece to this course, which has been all about doing linear algebra without the determinant. That is, the trace and the determinant, super cool tools, super useful. It wouldn't be a linear algebra course if we didn't introduce them. But most of the time in linear algebra, these things, because they're so useful and because they make certain things so easy, are brought up far earlier than they deserve to be, and things are done in terms of them instead of building from a more well-motivated background, and then at the end, showing that we have a nice way to do a bunch of things that doesn't require quite as much initial machinery. Skipping that initial machinery, though, gives you a far poorer understanding of what's going on, so that's why we waited until the end. All right, let's get into it. The trace. You've probably seen trace before. The trace is all about a connection between matrices and operators. Similarly, the determinant is the same kind of business. Let's do the trace first. It's a little bit easier. They're both pretty easy. That's why they're used so widely. But let's do the trace. So the trace of a square matrix, so an n by n matrix with entries in some field F, its trace, which we'll denote by TRA, is defined to be the sum of the diagonal entries of A. Here, quick example. This is not a hard concept, so we'll just do one example. Okay. Let's let A be the matrix. How about 3 minus 1, 2, 3, 2, minus 3, 1, 2, 0. Then the trace of A is just equal to, I'm going to pop a different color over here. Maybe I'll take something like a purple. So look at the diagonal entries, 3, 2, and 0. 3 plus 2 plus 0. It's 5. Bam. Okay, so the trace, just the sum of the diagonal entries. Easy stuff. All right, so trace. Trace is pretty nice. Here's a good fact. So let's suppose that A is an m by n matrix and B is an n by m matrix. Then if you multiply them together, you can get some nice matrices out, right? So one of them will be, well, if A is m by n and B is n by m, then AB is m by m and BA is n by n. So this says that the trace of AB and the trace of BA, two totally differently sized square matrices, are the same. Kind of crazy, actually. So let's do it. All right, let's prove this fact. This actually isn't that weird if you think about it. All it really boils down to is the fact that trace only depends on the diagonal elements, and diagonal matrices commute. So here's the idea. If A is equal to A11 through A1n, dot, 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 AN1, dot, 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 ANN, and B is equal to, let's do the same thing. A should be m by n, sorry, here. M rows, so yeah, I guess that should be an m right here, and this turns into an mn, there we go. And B is B11 through, dot, 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 B1m, dot, 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 BN1, dot, 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 BNM, there we go. Then here's the easy one, then I'll say it more specifically. Then trace A is equal to trace, I'll call it A tilde, and trace B is equal to trace B tilde with A tilde equal to A11 through AMN, dot, 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 0, dot, 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 0, dot, 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 dot. And really, I should be careful here because this is not exactly a diagonal. Well, here, let me do this a little bit nicer. So if these are both square, then I can make actually diagonal matrices. What I should be clear about is that I'm just going to take Okay. So this is not the proof in your book. I was thinking of a nicer case. I guess the one in your book is actually slightly more general than this easy, loose idea. So if these are both square, what I was going to say is this. So here, that's why my notes, I didn't have these as square. Okay, here. Let me make these n by n just for convenience, and I'll give you the nice intuitive proof, then we'll do the more detailed version. Sorry about that tiny confusion right there. Okay, so we'll make a tilde to be just the diagonal of a, and then zeros everywhere else, and zeros everywhere else. Okay, so this won't mess anything up, but it just only makes all that much sense if I take these ones to be diagonal in the first place. So I'm saying B11 now through BNN, and zeros everywhere else. Okay. So the trace of A and the trace of B are both equal to or respectively equal to the trace of A tilde and B tilde, since the trace only depends on the diagonal entries, right? Since A tilde and B tilde commute, we are done. Really, that's all it is. More precisely, here's all you have to do. So, the jth term on AB is diagonal, so that's ABJJ here, will be equal to the sum from k equals 1 to n of A jk, B kj. But all you really have to do here is notice that you're just multiplying some numbers. And hey, would you check this out? If you go across and you do this, okay, now all that this is, if you're fancy, is the following. So, trace of AB, well, it's equal to the sum of its diagonal entries. So this is equal to the sum from j equals 1 up to m, now returning to the non-square case for specificity, of k equals 1 to n of this whole thing right here. So this is A, j, k, b, k, j. And now, check this out. This is nothing. This is super easy to see. So if I flip and I sum from k first, and then I sum over j, b, k, j, a, j, k. Have I really done anything from the first one to the second one? No, those are equal. All I did is I flipped it. That is, it doesn't matter which order I multiply two numbers in, right? And if I'm taking a sum, I can take sums in whatever order I like. Yeah? Oh, whoa. Yeah, I can switch the order of these guys at will. This is just the trace of BA by exactly the same argument. That is, if the trace of AB is this, just flip out the A's and the B's, and then bada boom, you're left with this chunk right there. So that's the more precise version, but it's not as clear as noting that basically, like, hey, if it just depends on the diagonal part, diagonal matrices commute. Easy. All right, so here's a big question. How on earth do I connect the trace back to operators? That is, this is just defined for matrices, but we know that matrices, well, they can be matrices of operators. Is there some nice link between operators and their trace? And the trace of their matrices with respect to some basis? If there is, hopefully it doesn't depend on the basis, right? If it depended on the basis, then that would be sort of unfortunate. It would just become some sort of like an idiosyncratic statement about particular matrices as opposed to a statement about operators in general, which is what we've been trying to address this whole time. So here's the fact, as you've probably been staring at on the screen, that lets us do this. This lets us define the trace for an operator. It says that, hey, suppose T is an operator on V, finite dimensional vector space, and suppose that U1 through UN and V1 through Vn are two different bases of V, or potentially even the same basis. They're just two bases. Then the claim is that the trace of the matrix of T with respect to the basis U1 through UN and the trace of the matrix of T with respect to the basis V1 through Vn are the same. That is, that trace does not depend on the choice of basis. You can take the trace of an operator independently of its choice of basis just by taking the trace of the matrix of that operator with respect to any old basis you possibly want. So, if we want to prove this, it's not too bad. Here's all we need. So, let's let, for convenience, A be the matrix of T with respect to the basis U1 through UN. And let's let B be the matrix of T with respect to the basis, got my parenthesis too early right there, V1 through Vn. Just for convenience, so I don't have to write these matrix in this list every single time, right? Okay, here's the easy one. By the change of basis formula, back in chapter 3, way back a long time ago. Sorry to make you go way back to the past right there. There is an invertible matrix C such that the following holds. A is equal to C inverse BC. Okay, not too crazy, right? Thus, using the previous result, the trace of A is equal to the trace of C inverse BC, which is equal to, well, saying we're using the previous result, it says we can flip order. This is equal to the trace of C inverse CB, which is equal to the trace of B. Hey, look at that. Trace A equals trace B. That's what we wanted to show. Okay, so this will let us define the trace independent of a choice of basis and extend this notion that initially started just for matrices to operators. We'll see a cool connection to the spectrum of an operator next. Okay, so the trace of an operator, like we just said, is as follows. So if T is a linear operator in a finite dimensional vector space V, the trace of T, which we'll denote by TRT, is defined as the trace of the matrix of T with respect to any basis of V. Since, after all, the trace of the matrix of T with respect to one basis is the same as the trace of the matrix of T with respect to any other basis. We just proved that. All right, so what the heck is this thing? Here's the answer. It's actually pretty easy. So, on complex vector spaces, the trace equals the sum of the eigenvalues. On real vector spaces, it equals the sum of the eigenvalues of the complexification, right? So here's the idea. Proof. What we're going to do is we're going to say, hey, suppose that the field is the complexes and T is an operator on V, a finite dimensional complex vector space. The claim is that the trace of T equals the sum of the eigenvalues of T, each eigenvalue included as many times as its multiplicity, which, remember from the lectures last week, the multiplicity is the dimension of its generalized eigenspace, right? Okay, so let's roll through it. Here's the idea. Using the Jordan form, which we saw last time, there is a matrix, or I'll say there is a, I should start talking too fast. There's a basis of V for which the matrix there should be some kind of abbreviation for there is a basis of V for which the matrix, because we say it so often. But what a cumbersome acronym that would be. There's a basis of V for which the matrix of T is upper triangular and has on its diagonal its eigenvalues repeated as many times as its multiplicity. Oof. So since the trace does not depend on the choice of basis, using this basis delivers the result. And we're done. So really, all it's all about is the Jordan form, which we got last time. It says, hey, if you don't recall, Jordan form says that you have the matrix turns into this. It's a bunch of little blocks, right? Zeros everywhere else with AI upper triangular, lambda I just across the diagonal, all the way through, same one, and then some stuff up here. And this right here, this is dim G lambda I T, the dimension of the generalized eigenspace for lambda I of T, right? That's the size of this little block right there. Okay, cool. So, and lambda 1 through lambda m are the distinct eigenvalues, right? So basically it said, hey, you can't make every matrix diagonal, but you can find a way to turn it into a bunch of, you can make it block diagonal, and those blocks can be pretty nice, at least. They can be upper triangular and have just the eigenvalue on the diagonal as many times as the dimension of the corresponding generalized eigenspace. That is, its multiplicity. So, just using that basis, all you have to do is take the trace, you're summing up, hey, cool, you're done. So, what all this says right here, this says the following. You want like a specific formula. So, that if lambda 1 through lambda m are the distinct eigenvalues of T, then the trace of T is equal to, that's a weird T, let me make that less weird. The trace of T is equal to the sum from, I'll say I equals 1 to m of lambda I, but this should be repeated as many times as its multiplicity. Its multiplicity is the dimension of T minus lambda I, the identity, to the power dim V, which was the dimension of the corresponding generalized eigenspace. That is, this is just the sum from I equals 1 to m of lambda I dim G lambda I T, where G lambda I T is the generalized eigenspace corresponding to lambda I of T. Okay, cool. So we've got a formula for the trace. It's not too crazy. You can just write it down right there. It only depends on the eigenvalues. This makes some good sense. After all, the trace doesn't depend on any choice of basis. So removing a choice of basis, you're kind of only left with a little bit of information about T at all, which is its spectrum, right? So the trace is a purely spectral phenomena, essentially. it says that you can determine it almost entirely in terms of its eigenvalues. There's only this little extra multiplicative factor, its multiplicity right there, that tells you how many times each is included. Nothing too crazy. All right, cool. Here's our next claim, just tying things together. The trace is connected quite closely to the characteristic polynomial. So in the case of a complex vector space and T, an operator on it, supposing that vector space is finite dimensional, the trace equals the negative of the coefficient of z to the n minus 1 in the characteristic polynomial of T. Huh. Okay. Now, that's kind of interesting. So here, think about this. So, proof, not proof. All right, proof. We'll see that there is also, for the determinant, a similar characterization that ties both of them together. So, here we go. Suppose the field is complex, T is an LV, N is the dimension of V, and lambda 1 through lambda m are the eigenvalues of T. Okay. Then the characteristic poly of T is just z minus lambda 1 to the multiplicity of lambda 1, which is the dimension of g lambda 1 t, the generalized eigenspace, all the way down through z minus lambda m to the power dim g lambda m t. Okay, there we go. So, expanding, we get a polynomial of the form z to the n minus lambda 1 plus plus lambda n z to the n minus 1 plus a whole bunch of other terms plus all the way down to minus 1 to the n times the product. And I should be clear here, actually. I'm writing a little bit too fast right there. I forgot to write the multiplicities in this sum, since I'm only doing the distinct eigenvalues right there. So this is lambda 1 plus plus lambda 1 plus lambda 2 plus lambda 2 all the way up to plus lambda m plus plus lambda m. So this one is included dim g lambda 1, writing kind of poorly right there, lambda 1 t times, and this one is included, so on and so on, all the way down to the dimension of g lambda m t, so the dimension of the corresponding generalized eigenspace, that many times z to the n minus 1, and then there's a whole lot of other terms, and then we get down to the last little bit, which is the product piece, and this will give you lambda 1 lambda 1, so multiplied all together, and this is repeated dim g lambda 1 t times the dimension of the generalized eigenspace. Okay, and then more products all the way down to the last product, which is lambda m lambda m, and this is repeated the dimension of the generalized eigenspace times, and this is the constant term. Cool. Whoa. Oh, I guess I need a minus 1 to the n right there, just to be clear. Yeah. Okay, so here's another way to write this. Or if we let lambda 1 through lambda n be the eigenvalues of t with repetition according to multiplicity, we get the slightly cleaner form z to the n minus, make sure I'm writing this right, minus lambda 1 plus dot 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 plus lambda n z to the n minus 1 plus dot 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 plus minus 1 to the n lambda 1 product all the way down through lambda n. Whoa, nice. Same thing. I'm just saying, look, you can write it with respect to it being the distinct eigenvalues, or you can have eigenvalues repeated as many times as the multiplicity. All it is, and I'm not really showing this bit, but if you want to know where this comes from, you can just use the binomial theorem a lot of times, and it's not too bad. But we won't spend a bunch of time doing that. The whole point is just that, hey, if you trust me that we've done that tiny step of algebra correctly, all we're doing is we're taking a polynomial that's factored out nicely and we're expanding it. If you trust that I'm not lying to you about how to expand it, then all I'm saying is that one of these coefficients happens to turn out to be the trace. It's the coefficient on z to the n minus 1. It's this little chunk right here. This is the trace of t. Whoa. We're summing them up as many times as the multiplicity. Nice. Okay. What about the determinant? Let's start talking about it now. Okay, the determinant. Let's do it. So we're doing this a little bit different from this section in your textbook. It's a little bit more similar to the last edition of the textbook. I'm skipping some of the pieces on tensor products and alternating forms and stuff like that, just for time. And we'll instead just try to tie things to the determinant really quick. So what is the determinant? Definition. Let's do it. Okay, here it is. Suppose T is in LV if the field is the complexes, then the determinant of T, denoted det T, is the product of the eigenvalues of T, each repeated according to their multiplicity. If the field is the reals, then the determinant of T is just the determinant of T's complexification. So that is just treating it as the same operator but on a complex vector space. Okay, cool. So just in the same way that every real number is a complex number, we can do the same thing. Nothing big. So we just treat it as if it was an operator in a complex vector space. Bada boom. Easy. All right. Notice, fact, theorem, the following. So it's just the product of the eigenvalues repeated according to multiplicity. Well, hey, would you check this out? Remember when we were expanding out the characteristic poly and we saw, hey, look, the coefficient on the z to the n minus 1 term in the characteristic poly was negative the trace? Yeah. And then you got the constant term. It's some multiple, minus 1 to the n, either positive or negative, of the product of the eigenvalues, each repeated according to their multiplicity. It's the determinant. Whoa, wait a second. Theorem. I'll say the following. Here's how I'll put it. I'll basically say it exactly like the last one. So I'm going to make sure I say it exactly right. the determinant of t in LV is up to a sign, the constant term of the characteristic polynomial, writing terribly, of t. Oof, how about that? That's a pretty good theorem, isn't it? So it's the constant, up to a sign, it's the constant term of the characteristic polynomial. We box these since I've been boxing theorems anyway. All right, so it is up to a sign, the constant term. I'm going to say the proof there is straightforward because we've kind of already done it. So we'll say proof look at the last one. That is, if you just go back, as long as you trust that I'm doing this expansion correctly. And if you don't, I encourage you to just use the binomial theorem. You'll get there. This is exactly how we defined the determinant. Okay, so maybe this doesn't comport with your idea of the determinant you've seen. There's some sort of like, okay, we're taking some product, AD minus CB, BC. Yeah, okay, then we're going to do that a bunch for like submatrices with these pluses and minuses. You maybe have vague, fuzzy memories of how to compute a determinant, and it seems sort of nightmarish. We'll talk about that momentarily, but we're going to start by defining the determinant just in this way, and then we'll build back up to the piece where we did it before for matrices and show you that the weird way we calculate it for matrices comes from this definition. Okay, cool. But before we do that, which will be some of the main content, I would say, of the next lecture, what we'll do instead is I'll show you a piece that I think is really cool and neat to think about. So, first off, let's just get ready to think about the character, or let's think about the determinant. Here's another fact. So, probably falling over myself when I'm speaking right here. Oof. Let me see if I can write this nicely. Theorem. Okay. An operator is invertible if and only if its determinant is non-zero. Everyone knows this. This is not now a crazy fact at all. Why? By definition, the determinant of an operator T is 0 for T and LV if and only if 0 is an eigenvalue of T. Since a product of complex numbers is 0 if and only if 1 is. And the determinant is just a product of complex numbers. Its eigenvalues repeated according to their multiplicity, that is, repeated according to the dimension of their generalized eigenspace. All right, cool. So, the determinant is 0 if and only if 0 is an eigenvalue of T. Okay. Hence, the determinant of T equals, or is not equal to 0 if and only if 0 not an eigenvalue of T, which happens if and only if let's say this, T is invertible. I was going to maybe say it in a slightly more detailed way, but I think at this point you guys are all used to the line of reasoning that says, hey, if 0 is not an eigenvalue, then t is injective. And if t is injective and it's a mapping between vector spaces of the same dimension, then it also implies surjectivity, which implies invertibility. After all, every operator is a mapping between spaces of the same dimension. It's a mapping between a vector space to itself. So if you'll permit me to neglect writing that long chain right there and just rely on our intuition we've developed thus far, I think we'll be fine. So, okay, the determinant measures invertibility. Oh, wait a second. Does this let us determine eigenvalues with the determinant? Does this let us determine the characteristic polynomial and the multiplicities with the determinant? Yes, truth. So, theorem, and a good one at that. The theorem is as follows. Suppose that T is an LV, it's an operator on V. Okay, then the characteristic polynomial of T is the determinant of Zi minus T. Whoa. Okay, wait a second. This is cool. You can use the determinant to get the characteristic polynomial, and the characteristic polynomial gives you the determinant. Kinda neat. It seems like the characteristic polynomial has more information than the determinant. After all, the characteristic polynomial is just one term. The determinant is just one term in the characteristic polynomial, the constant term. But you can use the determinant of a slightly different operator to get back the characteristic polynomial. That's sweet. That's cool. They're tightly tied together. Let's prove this. This maybe seems surprising at first when you encounter it, but I'm claiming it's not actually that weird at all. And this proof is pretty easy. So, just to be clear, we're supposing that V is a complex vector space and T is an LV. If it's not, we're going to do the real version. I will say that at the end, but let's just skip the piece that talks about that at first. So here's the chain of reasoning. T, or maybe I'll say it this way. I'll say, instead of saying T has lambda as an eigenvalue, I'll say lambda is an eigenvalue of T. Well, I claim that that is equivalent to Z minus lambda is an eigenvalue of Zi minus T. Agree with that? I would say that this follows, if you don't believe it, from the following. It says that minus T minus lambda I is equal to, well, the following: Zi minus T minus Z minus lambda I. Do you agree with this? So if lambda is an eigenvalue of T, then T minus lambda I is 0 for the corresponding, T minus lambda I is an operator that zeroes out anything that lives in the eigenspace corresponding to lambda, right? Okay, so all we have to do is write that operator as something nice like this. Okay, hopefully everyone's cool with this piece right here. I've just got a Z minus lambda piece right there, yeah? Everyone good with this? Hopefully? If not, think about it for a second, and I think you'll see why this is true. Okay, so the determinant of Zi minus T is equal to Z minus lambda 1 through Z minus lambda n, where the lambda i's are eigenvalues of T repeated according to their multiplicity. Ugh, my tablet is lagging out. Maybe I'm writing too fast or getting near the bottom of my drawing surface. Oh. But this is just the characteristic polynomial. Oh, that's just the characteristic polynomial, right? It's got the eigenvalues as roots as many times, with algebraic multiplicity as many times as the multiplicity of that eigenvalue. That is the dimension of the generalized eigenspace. So just to address this piece right here where I said suppose V is complex and T is an LV, what I should say is that if the field is the reals, then the same argument holds with T replaced by T's complexification. Yeah? Okay, so nothing too crazy right there. So basically it's saying like, hey, if you were in a real vector space, then you might not even have any eigenvalues, so this doesn't make that much sense right here. So we'll just do it with the complexification of that operator on a real vector space, and then wouldn't you know it, since the determinant is defined for the complexification of a real an operator on a real vector space, we've now got what we want. So nothing too crazy right there. Basically just, if it's not complex, act like it is, and then you're good to go. So the characteristic polynomial can be derived from the determinant, and the determinant can be derived from the characteristic polynomial's roots. It's actually pretty cool. Okay, now let's hook the determinant and the trace together. Okay, so we're going to finish up today by hooking the trace and the determinant together. And I'll show you that in a certain sense, the trace is the rate of change of the determinant, or a small perturbation at zero. So let me write the theorem, and then I'll talk about what I mean by that. So theorem, here's the claim. Okay, here's the idea. Let T be an operator on V and define G from F to F by G of X is equal to the determinant of the identity plus X T. Then G prime of 0, the derivative of G evaluated at 0, is the trace of T. Whoa. Okay, check this out. So, what this is saying is that the trace is the derivative of the function that takes the determinant of the identity perturbed by a multiple, an x multiple of T. So as you plug in some value, it says, hey, take the identity and shift it by in the direction of T by some little bit where X is the little bit, right? So if you go in the direction of T from the identity, just moving a little bit away, right? Then the trace is the rate of change at 0. That is, if you look at just the identity and you say, hey, if I start moving from right here, what is the slope of my tangent line, right? So at 0, the determinant is 1, right? So how is it changing as I start to move in the direction of T from the identity? How is that determinant changing from 1 as I start to move towards T? The answer is that the rate of change is the trace. The trace is telling you how quickly, if you start at the identity your determinant changes as you move towards that operator. That's kind of cool. Okay. It also lets you recognize the trace as a derivative of a determinant, which is kind of weird. So, it all kind of comes together in a nice way, doesn't it? Here is a proof. So, notice that I plus xt has eigenvalues. Ooh, more lag. 1 plus x lambda 1 through 1 plus x lambda n, each repeated. Why am I lagging so much? Sorry about this, guys. According to their multiplicity. That is, according to the multiplicity of each eigenvalue for t, right? Yeah, okay, and it's going to be the same multiplicities for I plus xt, yeah? Okay, so watch this. So g of x is then equal to, well, it's the determinant of this thing. It's just going to be 1 plus x lambda 1 through dot 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 1 plus x lambda n. And now we'll just do a little bit of calc 1. Check this out. G prime of 0, well, this is the limit as x goes to 0 of gx minus g of 0 over x minus 0. Yeah? Nothing too crazy right there. This is just looking at secant lines, and we're taking the limit of progressively closer points until we get to a tangent line, right, in the limit. Okay, so this is just the limit as x goes to 0 of, well, put in g of x right there. It's 1 plus x lambda 1, product all the way down through 1 plus x lambda n. Got repetitions there according to their multiplicity. All right, minus, what is g of 0? Just plug in zeros for x. It's a lot of multiples of 1. So minus 1. And this is all over x. Okay, all I need to do now is expand out this big product. A bunch of the terms don't matter. Mainly what really matters is that I'll have a constant term. That is a term not involving x's, and that term will be 1, right? So take all the 1s. When they all get multiplied together, you'll get a 1. Cool. And then you'll get an x lambda 1 plus dot, 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 all the way down through x lambda n. This piece comes from when you take x lambda n times the 1 and x lambda 1 times the next one, right? You know, if you're doing these pairwise, it's whenever you take something with an x times one of the 1s. You add them all together, you'll get this piece. Okay, then there's a whole lot of other terms, and then at the very end, I'll have x lambda 1 product all the way down through x lambda n. And then I have my minus 1 at the very end. Wouldn't you know it, minus 1 cancels a minus 1. All of this stuff or I'll say has x terms of degree 2 or more, right? Okay, and on the bottom I still have my x. And so I end with the limit as x goes to 0, dividing my x's from here. That is, I'm going to cancel some x's, boom, boom, with this one right down there. And I'll just get lambda 1 plus dot, 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 plus lambda n plus, and then these ones right here will have, you know, I'll say stuff with x's, stuff that's multiplied by x's. Okay, and this just turns into lambda 1 plus dot, 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 lambda n, which is the trace of t. How about that? Everyone follow that piece? Basically, all it is says is, hey, look, g of x looks like this. There's a constant term. It's equal to 1. The term next to x just has lambda 1 through lambda n as its coefficient. Lambda 1 plus lambda 2 all the way up to lambda n as its coefficient. And then all the rest of the terms have higher powers of x. When you divide by x, they'll still have x's. So those ones get zeroed out by this limit. This piece right here is the only part that survives. The constant terms cancel each other out. You just get back the trace. So the trace is the rate of change of the determinant as it moves from the identity, or as it moves from the identity in the direction of your operator. Maybe I should say is the rate of change of the determinant as it starts moving. Just to be clear that I'm saying it's as it starts moving. That's clearer. So if you take the determinant of the identity plus some multiple of your operator, then at 0, that's just the determinant of the identity. And as you start moving towards your operator or minus your operator, doesn't really matter. What I'm saying is that the rate of change at that point, at the identity, how quickly this thing is changing, is the trace. Kind of neat. So there's a formula that ties together the trace and the determinant. Here's a fun little note. A little fact. There's a much fancier version of this that is known as Jacobi's formula. There is a fancy version of this known as Jacobi's formula, which says the following. That if a of t, even right like this, if a is a function from R to LV, then d dt of the determinant of a of t is equal to the trace of something called the adjugate, adj, of at times dA dt of t times its derivative. Oh, whoa, crazy. So in they'll say where adj a is the adjugate of a. You don't have to care about what the adjugate is. All I'm trying to say is that, hey, in case you found this interesting, there is actually a strengthening of this, which says that there's nothing special about the fact that we chose the identity plus xt. You could move at like a different rate. There would just be a corresponding slight variation in like the factor of that appears in that trace, right? So like if you went at like the identity plus x squared t, right? You went at a quadratic rate or something like that. It's essentially the same thing. There's not like some clever trick that I've employed to give you this formula that results in the trace. Indeed, the determinant and the trace are always tightly connected in exactly this way. And don't worry about what the adjugate is. You can look it up if you ever needed it. You don't need it for anything in this class. I just thought I'd let you know that there's a cool generalization of this result that holds more broadly than what we talked about. So next time, we'll get back into determinants a little bit. We'll return to what you're probably familiar with, this weird formula with alternating signs and small determinants and so on. determinants of submatrices. We'll talk about that next time. We'll wrap up the determinant, but this one was a fun one where we tie trace and determinant together. So I'll see you then. Have a good one.